If you walk through the old streets of Cognac in France, you will notice something. Many buildings and rooftops here are covered in a layer of deep black. Lift your eyes up. There, you will see a slender metal wire, only about as thick as your finger, suspended above you on steel poles. It looks fragile, almost weightless, compared with a train weighing thousands of tons rushing toward it. But do not let that appearance deceive you. This wire is the lifeline of an entire system. On modern railway lines, it carries alternating current of up to 25,000 volts. So, how does one tiny, constantly vibrating touch at 300 kilometers per hour not turn into a giant iron, melting everything in its path? Welcome to Everyday Things Explained. Touching is not enough. Our intuition usually tells us, if you want to conduct electricity, just let two metal objects touch. But in railway engineering, touching alone is a potential disaster. Imagine that the train never runs on a perfectly flat surface. It vibrates. It is hit by storms and wind, and the overhead wire always sags between two poles. If the pressure from the current collector against the wire is too weak, it will lose contact again and again. Every time a gap opens, a powerful electric arc leaps across, creating terrifying heat, hot enough to melt the metal surface. But if the pressure is too strong, to guarantee contact, friction will grind down that expensive copper wire so quickly. You would have to replace thousands of kilometers of wire every month. So, the problem here is not conduction. It is pressure management. The arm that listens. The device on the roof of the train that carries this responsibility is called a pantograph. But instead of seeing it as a rigid arm, think of it as a pair of ears, listening to the track and listening to the wire. It is designed with pneumatic cylinders, acting like extremely sensitive shock absorbers. It reacts constantly to every change in the wire. The wire sags downward, the arm pulls back. The wire rises upward, the arm reaches out. It is like placing your hand gently on a friend's shoulder while both of you are running. You do not push them over, and you do not let your hand drift away. The sacrificial piece. But no matter how perfect the pressure is, friction still exists. And this is where engineers make a surprisingly practical choice. They choose one part to die for the whole system. This contact strip is usually made from carbon graphite. Yes, it is the same kind of material found inside your pencil, but reinforced to withstand enormous electric current. Carbon graphite has a self-lubricating property. As it slides, it releases a thin layer of dust, helping reduce friction. Instead of allowing thousands of kilometers of copper wire to wear down, they let this carbon strip wear first. In engineering, protecting a system does not mean making everything immortal. It means choosing the right thing. That is allowed to be sacrificed. To save what matters most. This lesson is also very ordinary in life. Do not let yourself carry all the pressure of life. Create healthy sacrificial parts, such as drafts, checklists, or short breaks, so your main system does not collapse. The wire does not go straight. But there is a problem. If the wire ran perfectly straight, it would carve a deep groove right through the middle of the carbon strip. To solve this, engineers created a visual trick. If you look carefully from below, you will see that the wire is not straight at all. It runs in a zigzag pattern from left to right, then from right to left between the poles. This technique is called stagger. This slightly wandering path forces the wire to sweep evenly across the entire surface of the carbon strip as the train moves fast. That helps it wear flat and wear evenly. An old invention learns to run fast. The name pantograph did not actually begin with railways. It was a drawing tool from the 17th century, used to copy images. Engineers realized that the geometry of these linked arms was extremely stable for keeping one contact point balanced. Louis Faiveley refined it into a compact Z-shaped form, helping a French electric train reach a speed record of 331 kilometers per hour at the time. A silent agreement. In the end, the secret of high-speed rail does not lie in any magical material. It lies in an agreement between three elements: an arm that listens, a graphite strip that accepts wear, and a wire that moves off-center. A good system is not a place without pressure. It is a place where pressure is distributed intelligently, so that no single point breaks. Next time you wait for a train, look up. That wire is not fragile at all, and its deviation is actually a calculation full of art. Basically, railway engineering invented a way to go off course while still following the procedure perfectly. Thank you for watching Everyday Things Explain. See you in the next episode.